Thank you very much for the kind introduction and for the invitation. As announced, I will be talking about the Paris Agreement-compatibility of CO2 capture and utilization technologies today. But before that, I'll also just take the chance to tell you a little bit about climate change mitigation in general and about where we are now based on the IPCC report that was indeed published last month. And after that, I will go into the role of CO2 capture and utilization in climate change mitigation. So just a few highlights, because I'm obviously not going to be able to cover the entire IPCC report. But this report is talking about where we are in terms of greenhouse gas emissions, also where we are headed, and what actions we can take in order to limit global warming. So where we are now is that greenhouse gas emissions, so those are causing global warming, are currently at their highest level in human history. It's 12% higher than they were in 2010, and about 54% higher than they were in 1990. So we're not on track to limit global warming to 1.5 degrees, but we do see some evidence of climate action and that it has some effect, because the average annual growth rate of global emissions has slowed in the last decade. So while we're seeing 2.1% growth per year in the first decade of the century, so between 2000 and 2010, the growth was now 1.3% per year between 2010 and 2019. So there is some progress, but unfortunately the assessment concludes that, well, unless there are really immediate and deep emission reductions across all sectors, 1.5 degrees will quickly be beyond our reach. So the graphic that I showed before was about historic emissions and things that have already happened, but we can also use models to project what our emissions is going to be if we just keep on, if we don't implement additional policies compared to what we have already implemented. Because if we look at those implemented policies and we don't strengthen climate mitigation action, the greenhouse gas emissions are projected to lead to a global warming of 3.2 degrees by the end of the century. But what we can also do is use models to see what is needed to limit global warming to 1.5 degrees, or for example, 2 degrees. So that red line would be the current policies you can see in the graphs. But if you see like the blue areas and the purple areas, those are for 2 degrees or 1.5 degrees pathways. And what we see in those model pathways is that global greenhouse gas emissions need to peak immediately to limit warming to 1.5 degrees. And those are reduced by 43% in 2030 already. And if we only look at CO2, then we see that CO2 emissions reach net zero globally in the early 2050s. While for limiting warming to 2 degrees, so greenhouse gas emissions would need to peak also pretty much immediately, but would only need to be reduced by 27% in 2030, well, only. And the CO2 emissions globally would need to reach net zero in the early 2070s. Well, that's a big challenge. And for this to happen, emissions need to be reduced in all sectors. So that's in the energy sector, the land use sector, the industrial sector, in urban areas, buildings, transport, and also in terms of our demands and services. I will only look at the industry sector for now. So for the rest, I'll refer you to the IPCC report. Well, industry was assessed by Chapter 11, and industry is a sector that accounts for roughly a quarter of global emissions, and they have been growing faster than in any other sector since the turn of the millennium, mainly driven by the increased extraction and production of basic materials. And achieving net zero in the industrial sector will be challenging, but according to the report, it will be possible. And it requires a lot of different things, from using materials and energy more efficiently to an increased focus on reusing and recycling, minimizing waste, but it also requires a shift to new production processes electrification, use of hydrogen, for example, bio-based feedstocks, but also the capture of CO2 and afterwards storing the CO2, as well as the CO2 capture and utilization. And that is what I will be talking about now. So now I'm shifting the focus to the paper that we recently published. It's the title was Limits to Paris Compatibility of CO2 Capture and Utilization. And that was not just my work. I wrote that together with a lot of colleagues here from the Department of Environmental Science. So first of all, what is CCU? So CO2 capture and utilization. We defined it as a process in which CO2 is technologically captured from CO2 point sources or from air and is subsequently used in or as a product. And for this, I made this infographic and I tried to, because yeah, so realize that CCU is not one specific technology. It's more like an umbrella term for a lot of different technologies, and they can use CO2 from different sources. So either from the air or from a point source, like for example, an industrial facility or from a power plant where we use biomass or fossil fuels as feedstock or as fuels. And the CO2 can, for example, be combusted and you can have CO2 in the flue gas. So CO2 from air you can capture using direct air capture facilities, and those are mainly still in development by a lot of different companies. But CO2 from flue gases can be captured using, for example, chemicals or membranes, or they can be captured using microalgae cultivation. And then the CO2, then you have the CO2, and you can either use it directly, for example, in greenhouses. So the CO2 there can be, yeah, it's used to elevate the concentration of CO2 in that greenhouse. That facilitates increased plant growth. Or it can be used for enhanced hydrocarbon recovery. So then the CO2 is injected to, for example, oil fields that are almost depleted to increase oil production. It's also a form of CCU. But then CCU can also be used indirectly, which means that you convert it into something else. For example, mineral carbonates and building materials, or fuels, or for example, chemicals like plastics. And the idea is that all these CO2-based products can substitute fossil-based products. So like in the example of a fuel, if you use a CO2-based fuel instead of, for example, gasoline. And then the last thing is that these products are characterized by different lifetimes, which is the time that the CO2 stays stored in the product. So this can be a very long time or almost permanently in, for example, building materials, but it can also be quite short. For example, if you make this fuel, then if you combust it, the CO2 is afterwards again emitted after, well, let's say a few days or months. So that is CCU, and CCU sounds very appealing, right? It's creating a value or valuable product as part of the circular economy from something that we consider a waste. It's also something that a lot of different companies are developing, and the photo that I'm showing here is, for example, from X Prize, where I think was last year, where there were, for example, 10 finalists of technology developers getting a prize for good CO2-based technologies. However, many of these technologies are very energy intensive. So that means that they require a lot of energy to make a product from the CO2. Furthermore, CO2 is often released again after the use of this product, and many technologies are not yet market ready. So based on everything I told you from the IPCC report, we were wondering whether CCU can reduce emissions by enough, because we know we need really deep emission reductions, and whether CCU technologies are ready on time, because we also know that these deep emission reductions are needed very quickly. And together, these two questions sort of came to our main research question, which is whether CCU is Paris compatible. All right, a sip of water. So as an overview of the methods, we first developed Paris compatibility criteria. Because obviously, if we want to be able to answer whether CCU is Paris compatible or not, we need to know what the criteria would be for that. And then we gathered emissions data from different CCU routes based on life cycle assessment studies. And I'll tell you more about that a bit. And then we matched that with data on the maturity of these technologies based on their current technology readiness levels. So first, a bit more on the Paris compatibility criteria. We developed these based on emission pathways from the IPCC Special Report on Global Warming of 1.5 degrees. So these emission pathways limiting global warming to 1.5 degrees have two very, two characterizing numbers. The first is that in 2030, global CO2 emissions are halved compared to global CO2 emissions in 2020. And in 2050, global CO2 emissions are net zero. So that's pretty much in line with also the new scenarios and the new pathways that were published in the latest IPCC report. And based on these two numbers, we looked at what that would mean for the technology maturity and also the emission reductions that the CCU technologies would need to fulfill as criteria. And so first, for technology maturity, that was basically to be able to answer the question, are these technologies ready on time? And we looked at this for both 2030 and 2050. And for the technology maturity, is sort of the technologies that are new and they're developed and they go through different innovation phases. So we start out with a laboratory bench, and then you have a mini plant, a pilot plant, a demonstration plant, and in the end, full-scale plants. And to be able to communicate how far your technology is in its development, a scale was developed already quite some time ago. It goes from 1 to 9 in technology readiness levels, where 1 is really only basic principles observed, and 9 is a fully operational system at the large scale. And we found in the literature that, at least for the chemical industry, TRL 6 is often mentioned as the TRL from which it would take about 10 years until TRL 9. And TRL 6 also presents a turning point in the technology development because it requires an operational system at a relevant scale. So that means that for technology maturity, we say if a technology is in at least TRL 6 in 2020, it has a reasonable chance of having evolved to TRL 9 in 2030. So that's the first criterion. And for 2050, we say, well, it can be in any technology readiness level because it's still quite a lot of time and it has a lot of time to further develop. But then in terms of emission reductions, we also have criteria for 2030 and 2050. And the first one is that the emissions of the CCU product, so what we call here eCCU, the emissions of the CCU product, compared to the emissions of the substitute should be reduced by at least 50%. So eCCU divided by eSubstitute should be smaller than 50% or equal to 50%. That's because of the halving of emissions in 2030 compared to 2020. And then emissions of the CCU product need to be 0 or smaller than 0 in 2050. And like I said before, we use life cycle assessment to evaluate the emissions of the CCU product. And life cycle assessment is a systematic method to quantify and evaluate the potential environmental impacts of products throughout their entire life cycle by compiling all the environmental inputs and outputs. So in this figure, you basically see the traditional circle that you need to go through in life cycle assessment, and starting out with compiling all the inputs and outputs for the raw material extraction and production. And you consider the manufacturing, packaging and distribution, the use of the product, and also the end of life. And then specifically for CCU, we gathered a lot of life cycle assessment studies that had been published before. So we did not conduct a life cycle assessment of technologies ourselves, but we looked at all the studies that have been published before, and we selected data for 74 different CCU routes from the studies. But these studies were not very easy to compare. So we still had quite some work to do in order to make them comparable and in line with each other. So that's what we call the harmonization. And there we harmonized the system boundaries. For example, a lot of studies did not include the use of the product. So for example, if you make a CO2-based fuel, then many studies did not necessarily include that this fuel is combusted and then again emits the CO2. So we had to make sure that we harmonized that to be able to include all that. And then we harmonized the functional units. And that is the unit in which all the inputs and outputs are expressed. So if we look at the emissions of the product, we wanted to have everything in emissions per kilogram of CO2 utilized, because that's the thing that all these CCU routes have in common, that they're utilizing the CO2. And then the hydrogen source we harmonized because many fuels and chemicals require hydrogen as an additional input. So we made sure that those were all from electrolytic hydrogen. And then a very important part was the electricity, because a lot of electricity is used in the conversion processes, in the capturing and in the conversion steps of CCU. So we made sure that all the electricity that was used was in line with such an emission pathway that I showed before. So a pathway limiting warming to 1.5 degrees. And in 2030, the footprint of electricity would be 0.17 kilograms of CO2 per kilowatt hour. And in 2050, zero. So zero emissions electricity. And that's what we also assume for all the processes. And then there's something else, which is called multifunctionality. And that's kind of at the heart of CCU, because like I said, we're looking at all the inputs and outputs in a life cycle assessment. But CO2 is, in many cases, both an output, because it's something that comes from in primary production process. But it's also an input to our process for CCU. So how we had to deal with this dual function of CO2 was something that we talked about actually for quite some time within the research team. And I'm going to try to explain how we did that. So we did it differently for 2030 and 2050. So in 2030, we used a method that's called substitution. And there we assume that if you have a system, so looking at this figure, basically at the A part, you have a steel factory producing steel. And instead of the CO2 that would otherwise be emitted going into air, the blue box says capturing. So we're capturing that CO2. Then that CO2 is converted into a fuel, and the fuel is used in the car and then released again. Well, this system we call the point source CCU system. And we're assuming that this system substitutes B, so the system without CCU or without capture. And that means that we credit the CCU products for the avoided emission. So we say, because we deploy the CCU, we're avoiding that the CO2 is going up into the air. And that means that in our equation to determine the emissions associated with the CCU product, so ECCU for emissions of the CCU product, we have a minus for E utilized. So we subtract 1 kilogram of CO2 per kilogram of CO2 utilized to arrive at the final emissions of the CCU product. So we add the capture process emissions, the conversion emissions, and any other kinds of emissions that happen in the process, and again also the release of the CO2. But for 2050, we are looking at Paris compatibility of CCU, and we're assuming that a Paris compatible 2050. That's also why we are using zero carbon electricity in our system. But that would also mean that we can no longer assume that in 2050 we have these unabated fossil point sources to substitute. So we cannot assume that there would still be this, in this example, this steel plant that hasn't had any kind of changes compared to now, and that hasn't also reduced its emissions, and is simply still emitting in the way that it is emitting now. So we cannot credit the CCU product anymore for the unabated, for the avoided emission. And this is the case for fossil CO2, so for fossil point sources. And then the equation would be different for eCCU. So then we assign all the emissions to the CCU product from the point of capture. So the capture losses, the capture process, the conversion, and the release of any of the CO2 that would be included in the product. For atmospheric or biogenic CO2, we still use the equation that we had for 2030, because these sources would still be available in 2050. Okay, then the results. What we see here in this figure is technology readiness level on the x-axis. So for all the technologies, we see where they are in terms of their technology maturity. And on the y-axis, we see the greenhouse gas emission intensity ratio of CCU products. So this is for 2030. And everything that's in the gray area fulfills our Paris compatibility criteria for 2030. So that's on 8 out of the 74 routes. And these CCU routes are characterized by storing CO2 permanently, because that would mean that the CO2 is not released. So as part of the equation, that term doesn't add anything. And they're also characterized by replacing a greenhouse gas intensive fossil product, because it's about the ratio. And what I think is important to also note in this figure is that many CCU routes do not reduce emissions compared to the substitute. So everything that is above the 100% is, for those CCU routes, the products are emitting more than their fossil counterparts. And that is mainly due actually to the electricity use. So we have, like I said before, in 2030, not assumed that the electricity is emissions free, but the electricity footprint is in line with a 1.5 degrees pathway. So it has been reduced a lot compared to now, but it's not emissions free. And if you use a lot of energy, that would still make that you have a significant footprint. And then for 2050, we have not included the TRLs in the figure because they did not, because they don't matter for our Paris compatibility. So we simply plotted the greenhouse gas emissions intensity of the CCU products in 2050. And here we see 4 out of the 74 routes that are strictly Paris compatible. There's a couple of others that are sort of in the surrounding area of zero emissions. And for routes to be Paris compatible in 2050, they need to fulfill 2 out of 3 criteria. And those 3 criteria are that they use biogenic or atmospheric CO2, that they store the CO2 permanently, and that they have a carbon neutral capture and conversion process. So a few examples are that if you would have a fuel, then you would need to use biogenic or atmospheric CO2, and combined with a carbon neutral capture and conversion process. So all the energy and all the other processes that you would need during the capture and conversion would need to be completely carbon-free or greenhouse gas-free. So that's quite a challenge. So some conclusions from what we have from our research are that there are actually quite few of the routes are Paris compatible, and that out of the 2030 Paris compatible routes, 7 out of 8 do not meet the 2050 criteria as well. So this could potentially lead to a lock-in. And a lock-in means that you do a lot of investments right now into changing your processes and infrastructure to improve them, and that would help for the short term. But if you're already doing all your investments now, and especially if you look at the chemical industry, and they have huge installations, and this could lead to a problem if you've already invested a lot in just some incremental improvements, and which would not be good enough for 2050 or for the long run. So we also see that using fossil CO2 in products with non-permanent lifetimes is not Paris compatible in the long run. So it might also be good to, if we would use fossil CO2 in the short run, to look at how we could make a switch to non-fossil carbon for those products in the longer run. And in general, I think it's very important to consider which sources of CO2 we use. Also look at really the emissions throughout the capture and conversion processes. So the whole production process of the CO2-based product, as well as considering the lifetime of these products. And all that needs to be considered to evaluate the CCU technologies in a fair way. And for future research, there's quite a few things that I think would still be interesting for us to do. And the first thing that I'm looking at right now is whether CCU can be used to achieve CO2 removal. And CO2 removal is effectively lowering the atmospheric concentration of CO2. And this is something that we will need. It's something that comes out of all the emission pathways limiting global warming to 1.5 degrees or 2 degrees as one of the strategies that to achieve those goals. So I'm interested in whether or when CCU could help in this, what the conditions would be. But what we have not done in this study is compare CCU technologies to other technologies that could replace the production of fossil products. And this could shed light on some trade-offs between options and might also change the verdict on some routes that are close to the emissions frontier, because they might just be the best that we have. And furthermore, I think it's very important to look at how we can use scarce resources in the best way. Like, how can we achieve the best optimal environmental outcome? Because one of the 2050 Paris compatible options is using atmospheric CO2 to produce a fuel, for example. Well, it takes a lot of energy to capture that CO2 from the air and then convert to make a fuel out of it. Would that be the best use of our green electricity, or would it be better to use that green electricity directly, especially in the coming time when we are still decarbonizing the electricity grid mix? It's quite clear that that's probably the best thing to do first with our electricity. But then what are the alternatives? How would it compare to, for example, only hydrogen production and using that hydrogen directly? So I think that is a very important thing to look into further. And regarding that, the importance of the electricity footprint in different mitigation options, there's a few examples that I still wanted to show. And this is based on not my own research, but it's based on research by Niall McDowell and his group published last year, where they look at different hydrogen production routes. And what you see here is that the green line, that is hydrogen production from water electrolysis. So using electricity and water to produce hydrogen. And on the x-axis, you see the carbon intensity of the electricity. And on the y-axis, you see the carbon intensity of hydrogen. So it's directly, so how green the hydrogen is really directly depends on the electricity that you put into it. And for example, you see the Netherlands somewhere in the middle of the graph. And if you compare that then to gray hydrogen, which is hydrogen based on natural gas, and that's the conventional way of producing hydrogen, that's the gray line, the green. Well, obviously, we should not be using our current electricity mix in the Netherlands to be producing hydrogen, because it has a much higher footprint than current fossil, like natural gas-based hydrogen. The blue bar is for using a natural gas-based hydrogen compared with carbon capture and storage. So here you see that how important it is to consider the carbon footprint of electricity. Because it really affects whether or not whether or not electrolytic hydrogen is a good idea or not. So because, for example, if you use the Swedish mix, so that's SE on the graph, then it is much better than the conventional ways of producing hydrogen. And in this graph, you see on the left-hand side, whether or not using electricity or using electric vehicles instead of conventional cars reduces emissions or not. And on the right-hand side, you see whether heat pumps instead of conventional heating would reduce emissions or not. And this was published a few years ago by my colleagues here at the department. And the green indicates in which locations this would indeed reduce emissions or not. And it's also again done for 2030 and 2050, and also based on a current policy trajectory, but also a 2-degree scenario. And it all actually doesn't matter that much between all these different scenarios, because almost everywhere already now, but definitely in a few years' time, electric vehicles or heat pumps or using their electricity mixes would reduce emissions. But this is actually the other way, another kind of example where it appears not to have such a big difference. It's already a good idea either way, regardless of the electricity mix and the changes that we make in that. And then as one other final example, it is about direct air carbon capture and storage. So that is about directly capturing CO2 from the air, and whether or not this would be a good idea or not. Because in the left-hand, leftish bar, that is for, we're again looking at different locations. And if it is above the zero line, then emissions are increased by deploying this technology. So instead of capturing CO2 from the air, we're actually adding CO2 from the air, and that is the case in some areas right now. While in other areas, we are going negative. And you can also see that over time, and also using different kinds of assumptions for this and for the pathways that we are going to take as a world, well, very quickly at least, everywhere around the world, this based on different kinds of electricity mixes, this would indeed start reducing emissions or removing CO2 from the air. Yeah, so there you really see how the carbon footprint of electricity can, as one factor, have a very large impact on deciding whether a technology does or does not reduce emissions. And that leads us to the takeaways. Well, some technologies or strategies that are aimed at reducing emissions may sound very appealing, but an assessment of their direct and indirect environmental impacts may reveal the contrary. And scenario analysis can be very useful to understand how emissions depend on factors that are uncertain or that could develop in different directions. And lastly, I think life cycle assessment can really help to clarify under what conditions or in which contexts technologies can achieve their optimal outcomes. which could possibly help in the design of policies to create those kinds of conditions and facilitate the transition. Thank you very much. If you have any questions, please let me know.